Hello, my name is Nicholas Athanasios Anagnostopoulos and I will be the moderator for this session. I would like to welcome you to the second day of the IEEE Computer Society DVP SYP virtual conference on hot topics in cybersecurity. This session is on the security of cyber-physical systems. The Distinguished Visitors Program was initiated in 1971 by Dr. Stephen Yao and offers top-quality speakers to professional and student chapters. The Student and Young Professionals Activities Committee was developed to support the Computer Society students and young professionals globally through initiatives targeted at advancing their knowledge, development, and careers. Before we get started, I'd like to get a couple of housekeeping tasks out of the way. You can ask your questions in the Q&A panel. Dr. Sengupta, Dr. Singh, and Dr. Punya will answer as many questions as they can following their presentations. Our final speaker, Dr. Punya, is unfortunately not yet present, so this session may be a bit shorter or longer depending on his ability to join us. The session is being recorded and the slides and recording will be made available after the session. Please allow me now to welcome our speakers. The first speaker, Dr. Anirban Sengupta, is an associate professor in computer science and engineering at the Indian Institute of Technology in Indore. He is an elected fellow of IET and fellow of the British Computer Society. He holds a PhD in electrical and computer engineering from Ryerson University of Toronto in Canada and is a registered professional engineer of Ontario. He has been serving as an IEEE Distinguished Lecturer for the IEEE Computer Electronics Society since 2017 and as an IEEE Distinguished Visitor for the IEEE Computer Society since 2019. He is an ex officio member of the Board of Governors of the IEEE Consumer Electronics Society. He has more than 230 publications and patents. He is an author of 2 books from EIT on the subjects of IP core protection and hardware-assisted security for consumer electronics and Frontiers in Security IP cores, Forensic Detective Control and Obfuscation Techniques, published in 2019 and 2020 respectively in the United Kingdom. He is also the author of an edited book from Springer on the topic of PLSI design and test, published in 2020. I would like now to welcome Dr. Sengupta. I would like to pass the floor to him.
Thank you so much for the introduction. I would like to thank the IEEE Computer Society for inviting me to this event, and I take this privilege in giving my talk to the audience. Okay, so let me get started. Okay, so the topic of my talk is hardware security of integrated circuits for DSP and image processing applications. In today's talk, I will be touching upon the different algorithms that are often used in securing hardware, specifically in the context of digital signal processing cores and the image processing applications. I will also give a brief idea about the different hardware accelerators that are used in the real world, especially in the context of consumer electronics products, as well as in the applications of aerospace applications and military. So I'm going to be using the following books. These are my written books in the field of hardware security and hardware-based cybersecurity and IP core protection. So I'm going to use the contents of this book to talk more about the details. Okay, so what is hardware security and what is IP core protection? So hardware security and intellectual property core protection is an emerging area of research for semiconductor community that focuses on protecting designs against standard threats such as reverse engineering, counterfeiting, forgery, malicious hardware modification, etc. Now, hardware security can be broadly classified into 2 types. The first is authentication-based approaches, and second is obfuscation-based approaches. The later type of hardware security approach, which is obfuscation, can again be further classified into two categories, which is structural obfuscation and second is functional obfuscation, or often known as logic locking. Now, structural obfuscation transforms a design into a respectable form that becomes unobvious to an attacker, but is functionally equivalent to the original. This means that this is significantly more difficult to reverse engineer, while the second type of obfuscation approach, which is the functional locking or functional obfuscation, is an active mode of protection that locks the design through encryption or the application of secret keys. Okay, so now let's look at the examples of hardware accelerators that are often used in the real life. So hardware accelerators for popular DSP and image processing applications can be the following. For example, finite impulse response filter, FIR filter. We can have JPEG compression decompression IP, for example, JPEG Codec. That is what is popularly known as. We could think of convolution filters, for example, like image blurring filter, image sharpening filter, image embossing filter, and image edge detection filters. Now, image edge detection can be performed using Laplace edge detection, Sober filter, Previtt filter, and several others. The fourth type of hardware accelerator is discrete Fourier transform, and the fifth one is discrete cosine transform, and of course, we can have image brightness and contrast filter also. Now, why am I talking about hardware accelerators? Because hardware accelerators are an integral part of the consumer electronic applications, because they actually serve as the work engine for performing the data-intensive and data-crunching applications. Okay, so any type of data crunching or data-intensive application has to be converted into a dedicated hardware, often known as hardware accelerators or reusable intellectual property cores. Okay, so it's important right at the beginning to understand what these hardware accelerators are. And they are often used in several electronic products, such as in mobile phones, in digital cameras, in camcorders, in smartwatches, and so on and so forth. Now, there are different types of hardware security algorithms that have been researched and innovated by the scientific community. So I'm going to be touching about the following ones, okay, specifically the ones related to biometric fingerprinting and the ones related to cryptosteganography and structural obfuscation. However, the five most important ones in the context of DSP and image processing applications that have come out in the recent years are: first is cryptosteganography algorithm. The second is integrated watermarking and key-based structural obfuscation. The third is biometric fingerprinting. The fourth is integrated cryptosteganography and structural obfuscation. And the last one is key-based hash chaining algorithm. So I'm going to be talking about a few of these in today's talk. Okay, so in our research group, we have actually released a few in-house hardware security tools for handling hardware threats of forgery, false claim of ownership, detecting pirated designs, and blocking or hindering reverse engineering process. So some of the tools that we have released in September 2020 are, first is the CryptoStego tool. The second is KSOPW tool, which is again a structural obfuscation and physical level watermarking tool. The third is KHC Stego tool, which is based on hash chaining and steganography combined. And the last one is known as pseudo operation mixing based structural obfuscation tool. So all of these tools are actually used for countering the different types of hardware threats, such as I said, reverse engineering, malicious hardware modification like backdoor insertion of Trojans, or kind of like authentication of the actual IP owner, detecting pirated designs, and so on. Okay, so now let me move into a topic of IP core protection of DSP cores. Now this is a branch of forensic detective control, and why we call it a branch of forensic detective control is because they're often the final step of verification and authentication is often done through forensic analysis. Okay, so the major types of IP core protection for DSPs could be a single phase hardware watermarking approach, could be multi-phase hardware watermarking, could be multi-level hardware watermarking, and the last one is hardware steganography. There's a fifth branch, which is also known as digital signature-based watermarking, which is more robust and more secured, of course, than compared to single-phase hardware watermarking. So the difference between hardware watermarking and hardware steganography lies in the fact is that in hardware steganography of DSP cores, what we are basically doing is that we are embedding the embedded data through the application of stego keys, okay, in the covered design of the application itself. Okay, so there is no explicit signature that plays a role in getting embedded into the application. On the contrary, for hardware watermarking, what happens is the vendor specifies or selects a particular n-bit or n-digit signature that is converted into its respective artificial constraints, and then it is embedded into the DSP applications. Okay, so in simple words, we can think of hardware steganography as a signature-free mechanism and hardware watermarking as in-signature mechanism. Talking about the multi-phase watermarking and multi-level watermarking, the basic difference is in multi-level watermarking, we are actually embedding the watermarking constraints at different levels of the abstraction. Okay, so for example, some constraints could be implanted at their RTL level, some could be implanted at the gate level, some could be implanted at the electronic system level. While for multi-phase watermarking, we are actually implanting the watermarking constraints within a single phase. For example, this phase could be high-level synthesis, where we implant the watermarking in the register allocation phase, in the FU allocation phase, in the scheduling phase, or in the interconnect binding phase. Okay, so these are some of the examples where multi-phase watermarking could be implanted as. So that makes it clear how is multi-level watermarking different from a multi-phase watermarking. Now moving on, the digital signature watermarking method is basically more robust than a regular hardware watermarking approach. Why? Because we are actually doing an integration of the hashing process along with the encryption to generate the secret constraints that gets embedded into the design. Okay, so this is actually inspired from the digital certification process, where we have the hashing of the initial data done, and then we digitally sign it and append it along with the original document. So that's how this process of digital signature works. So this actually gives a very strong, robust proof of the authentication of the actual IP owner. Okay, so now let me move into the obfuscation part of the hardware security. So the obfuscation of DSP applications can be done by one of the following ways. The first is, of course, these are all, these have all come up in the recent years in the form of several publications in IEEE transactions and some in the books. So the first type is compiler transformation driven structural obfuscation of DSP circuits. So here we use some compiler transformation techniques and apply it on the data flow graph of the application that results into a functionally equivalent but structurally different DSP circuit of the original application. The second is on the high-level transformation based structural obfuscation of fault-secured DSP circuits. Fault-secured DSP circuits are often used in aerospace applications, and the reason it's called fault-secured is that it has ability to either detect a transient fault or it has ability to either tolerate a transient fault. Transient faults are quite different than intermittent and permanent faults, because in transient faults it just remains valid for a few picoseconds and then the error vanishes. So therefore it needs sophisticated algorithm to perform fault security and fault tolerance. So these fault-secured DSP circuits have the ability to detect fault, detection of transient faults, and thereby these circuits are also widely used in aerospace applications. So important, side of this is that these type of applications or circuits also needs to be secured against possible reverse engineering and possible backdoor insertion of Trojan by the process of structural obfuscation that actually thwarts these type of malicious backdoor logic insertions. The third type is also known as hologram-based structural obfuscation. Here what happens basically is that the integration of multiple applications of DSPs are combined together in one circuit in a camouflaged fashion. And the activation of a respective circuit is only possible by the application of the correct secret key, which is only known to the IP owner. The fourth and the fifth one, which is based on functional obfuscation, either with the conjunction of AES and SHA or without the conjunction of AES and SHA, is actually an active mode of protection that helps in encrypting the circuit at the gate level. Okay, so what I mean by that is you will actually apply a certain secret key. For example, it could be a 128-bit secret key or 256-bit secret key by employing IP locking blocks or locking logics at the circuit level, at the gate level, and only by the application of the valid sequence of those private keys, the actual functionality will be enabled. Okay, the reason for using SHA and AES along with it is to reconfigure those IP blocks and reconfigure those locking cells so that the attacker doesn't have a fixed template for these, and they will not be subjected to removal attack. Okay, if you have a reconfigurable architecture, then the attacker will not have a fixed template and would find it hard to identify which is the IP locking block. So this reconfiguration is performed by the output of the AES. Okay, and the AES output will only be governed by the 128-bit fixed secret key. Okay, so that's how it becomes difficult for an attacker in performing removal attack, along with performing key sensitization based attack, which is the attack used typically for logic locking purpose. Okay, now let me talk a little bit about the stegography model. Okay, so in stegography, what typically happens is that we implant a secret stego mark into the design. So if you have a brand X of the original IC, and if we can extract the secret mark from the brand X, then we would know that it is probably not a counterfeited version. And if we don't find the secret mark, then we could probably believe that it's a counterfeited version of the IC. While in order for detecting the IP or IC cloning, we have a brand Y, and in the brand Y, if we do find the secret mark or stego mark of brand X, then we know that it's probably a copy, else it's not. And in the context of nullifying the fraudulent claim of ownership, what typically happens is through the process of forensic analysis, we could find out the presence of stego mark into the design. If the original stego mark of the actual owner is present in the design, then the conflict resolution in the IP ownership will be proven. Now let me a little bit talk about where do we actually implant these hardware security constraints into the RTL or HLS framework. Okay, so let me talk a little bit about the high-level synthesis first, because that's what most of the work on these DSPs are based on, because HLS plays a very crucial role for DSP and image processing. So in case of high-level synthesis, we have a DSP system, and that interacts with and that connects through the scheduling, hardware, and register allocation phase binding, and followed by the multiplexing process, and then the data path and controller generation. And these hardware security framework that comprises of either the security algorithms in the form of watermarking constraints, stego constraints, these will all be integrated along with the HLS process, so resulting into an in-synthesis security design. Okay, so that means while the synthesis is going on, these algorithms will be implanted into the design. For example, in case of HLS, the security algorithms will be implanted while the register allocation process is performed or while the FU allocation process is performed. Okay, and finally, therefore, when we have an RTL design, it actually already comprises those secret digital evidence of the algorithm inside it, and then it is subjected to RTL logic synthesis to finally get to the gate level structure. However, if you're talking of logic locking, then of course we need to get to the gate level. Okay, we can of course append the IP locking blocks in the RTL design, and then we have to resynthesize it so that at the gate level we find those IP locking blocks all camouflaged with the existing gate level structure. So that's how the interaction between the security framework and HLS framework happens. Okay, so now we can talk a little bit about the digital forensics branch of hardware security. So securing hardware accelerators using biometric fingerprinting. Okay, this is a very important branch that have been recently studied, and some papers have come out in IEEE transactions on VLSI. So what it typically tells is that if an IP vendor's fingerprint can be converted through some sophisticated algorithm into its respective digital template, then that digital template can be encoded into the IC or IP, okay, either at the RTL stage or at the gate level stage, to form a secured hardware accelerator of the respective DSP or image processing application. Okay, and this could therefore thus provide a shield against false claim of IP ownership and piracy. Okay, so let's see what is that sophisticated algorithm and how it works. So suppose we start with an input fingerprint of an IP vendor, and once it is captured through an optical scanner device, it is then subjected to pre-processing, where in the pre-processing stage we have the FFT enhancement followed by binarization and thinning. In the FFT enhancement stage, what is typically done is that in the FFT transformed image that is obtained after we perform FFT multiplication of the matrix, then whatever the FFT transform matrix that you have, that for that each pixel values will be subjected to the calculation of the amplitude, and from that we can perform masking to obtain the masked matrix of the FFT enhanced image. Now this masked matrix is then further multiplied with the original FFT transform matrix to obtain an output, which is then subjected further to inverse FFT to get back to the original image. We need to perform the inverse FFT because we would like to get back from the frequency domain back to the spatial domain. Okay, so that's how the FFT enhancement works. And once the FFT enhancement is done, okay, the next task is to perform binarization. And binarization is nothing but sort of image segmentation, where the image has only two intensity values. And so therefore we can also call that as a binary image. And this image usually shows only black and white, where the black is represented by 0 and the white is represented by 255 if we are talking about a grayscale image. The basic principle of binarization is to compare the pixel intensities with the threshold, and thereby setting the pixels whose intensities are less than the threshold to 0 and the others to 255. Okay, but it's important to note that the binarization can only be performed after the FFT enhancement is over, because in FFT enhancement we actually allow the image to be enhanced. By the word enhancement, what we are referring technically is to reconnect the broken ridges first. Second is to finally separate the parallel ridges, and also to make the ridges thicker, okay, than what it actually is. So once the FFT enhancement and binarization both over, then we move on to the thinning process. In this process, the thickness of the ridge lines is reduced to 1 pixel width by deleting the pixels at the edge of the ridge lines. Okay, and once this pre-processing step till thinning is over, then we move on to the step of minutia extraction. The minutia extraction process works through the crossing number algorithm, where we have picked up basically two major types of minutia features. First is the ridge ending. Second is the ridge bifurcation. In a fingerprint image, if a point abruptly ends, I mean if the ridge lines abruptly ends, then it's a ridge ending, while if the ridge lines actually fork, that is it branches, then it's known as a ridge bifurcation. We employ the process of crossing number algorithm to extract the minutia extraction by using the CN value. So for example, if the CN value is 1, then we know it's a ridge ending, while if the CN value is 3, then we know it's a ridge bifurcation, so on. Okay, and once this minutia extraction is done, then we will convert this minutia point into its respective digital template by concatenation of 4 dimensions. The first is the X and Y coordinate, and followed by the minutia type, which is determined by the CN algorithm, and third is the ridge angle. Okay, now ridge angle is evaluated clockwise from the horizontal axis. So by the concatenation of these 4 dimensions, we actually arrive into the digital template, which is then further subjected to mapping through an encoding algorithm. And this encoding algorithm actually converts the digital template into its respective hardware security constraints. Now it's important to note here that there is a strong correlation between the digital template and the encoding algorithm that is used to convert it into its respective hardware security constraints. The reason is, first, the robustness of this correlation not only depends on the number of ones and zeros in the digital template, but it also depends on the sorted list of the storage variables in the colored interval graph of the DSP application. And it also depends on the number of storage variables, okay, which is again a function of the resource constraints that is either obtained as directly as a designer input or could be obtained through a process of design space exploration algorithm. For example, using particle zone optimization, or could be vectorial foraging optimization, and so on. So using a DSP system, these resource constraints are obtained that is further used to provide or determine the number of storage variables in the CIG of the DSP application. Now, based on the hardware security constraints that we have got, then we implant it into the DSP application using HLS framework to finally obtain a hardware accelerator design with the biometric fingerprinting. Okay, and therefore this biometric fingerprinting allows the designer to have, that is the basic IP owner, the main IP owner, to have three different properties. The first is it is non-replicable. The second is it has uniqueness, so it is not vulnerable to theft or leakage. And third is there is no direct requirement of storing it, as in the case for watermarking, for example. And this biometric fingerprinting process, okay, as part of digital forensics, is therefore very crucial in nullifying false claim of ownership and detecting pirated designs. Now, if you see the diagram here, we have an input fingerprint image, which is, we convert it into a binary form, followed by we have the thinning, and then we have the minutiae points. And this minutiae points, you may see 2-3 different colors, which actually represent the different types of minutiae features. For example, ridge lines, ridge ending, for example, ridge bifurcation, and so on. When we have the different fingerprint images, it can actually generate different types of minutiae point sizes. And from there, we can actually represent the digital template with different strength. So for example, a minutiae point of 22 converts into a digital template of 526 bits. A minutiae point of 15 converts into 350 bits, and so on. And depending on this total size of the digital template, which is known as strength of the digital template, we can also get the number of zeros and ones, which are then converted using an encoding algorithm for further implantation. Now, even for an individual, the different fingers can obtain, can be used to obtain different minutiae points and different strength of the digital template. And again, using that, we can again get the number of zeros to be different compared to, another finger, for example, for the same person. So this is one of the DSP applications of secured JPEG Codec that we've designed in our lab, which implants a biometric fingerprinting. Okay, now let me move to the section of how to detect biometric fingerprinting in a hardware accelerator. So it's quite simple. We have the digital template of the embedded biometric fingerprint that has to be fed along with the digital template of the genuine IP owner's biometric fingerprinting under test. If they both match in terms of the number of zeros and ones, okay, then we know that possibly this is a real owner. And then we go to the second condition box where the matching of the positions of the constraints, that is zeros and ones of the digital template, is also performed. If, of course, the first condition box is not satisfied, then it's a counterfeited design. While if both the conditions are satisfied, then the ownership is awarded to the true IP owner. Now, if we talk about the variation in the number of minutiae points for different fingerprint images, you can see that the minutiae points actually vary for different fingerprint images, as I've shown with the diagram in one of my previous slides. So this is certainly a possibility. And we can also have a variation in the total number of constraints for different fingerprint images. So the constraint sizes can also vary to a large extent, as you can see here, from 350 to basically 555. There's a huge variation. And using this, we can actually devise a mathematical metric, which is known as probability of coincidence, which actually tells you the probability of a unsecured design having the security constraints. For example, the probability of a non-watermark design having the watermark, or probability of a non-biometric fingerprinted design having the biometric fingerprint constraints by coincidence. Okay, so lower is the probability of coincidence, higher is the security, and more robust the algorithm is considered to be. Okay, so as you can see, the probability of coincidence for different fingerprint images also vary depending on what is the size of the security constraints obtained. Another important aspect when devising a hardware cybersecurity algorithm is the cost overhead. So therefore, if in the context of fingerprint constraints, if you are trying to compare the design cost of the baseline with the design of the JPEG compression hardware after implanting fingerprint constraints, we see that the design cost overhead is almost zero, which indicates that it's a very strong algorithm with minimal design overhead. Okay, so we are done with the biometric fingerprinting part of the IP core protection. I'll move to the next part of it. Now, let me talk about this stegography model. So the stegography model is basically part of hardware stegography, where you have an embedded block that takes in the cover data of the design, and the embedded data, okay, that will be implanted into the cover design of the data, will be controlled by the application of secret stego key. Okay, the secret stego key basically controls the amount of embedded data that will be implanted into the cover design. And based on the stego data that has got into, implanted into the design, can be again further used for extraction through the application of stego key to extract the embedded data out of it. The other algorithm used for performing IP core protection is known as key-triggered hash chaining-based steganography. This is also used for securing DSP cores and image processing cores. So the way how it works is as follows. You have the input application of the DSP in the form of a data flow graph, which can be obtained either by the transfer function or by the C code. Then you have the module library and the resource constraints, which is fed into the scheduling algorithm block to generate a scheduled DFG. And then by the application of several encodings that you have, which are all part of the parallel encoding blocks, we can feed the output of the encoding into the hash chaining block. Okay. Now the hash chaining block has two types of hash units. The first is a regular hash unit, and second is the key-driven hash units. The regular hash units range from hash unit 1 to hash unit k, and the key-driven hash units range from k+1 to twice k. In the hash unit 1 to k, which is a regular hash unit, the input from the encoding, okay, can go directly into the hash unit through a pre-processing stage and through bit padding block. The bit padding block produces an output of 380 bits, and the pre-processing of the first hash unit is performed as follows. So for example, if the input is 1024, so first the m-bit chunk of the actual operations of the DFG is then further appended with a 1 followed by a sequence of 0 bits to generate a collective 896 bits of the total application. And then the remaining 128-bit representation is actually the length of the encoded bit stream to produce a 1024-bit output. Okay, so that serves as the input for hash unit 1. And then for the remaining hash units, the 1024 bit can be formulated by the 512-bit output of the previous hash block and appending it with 1000 and the 120-bit representation of the length 512 bits of the previous hash. Okay, and this bit padding can be for the first k hash units can be directly got from encoding Z1 to encoding ZK, while for the remaining hash units, it will be an output from the parallel switch blocks which are controlled by the stego key. Okay, and this goes through the process of hash chaining block to produce a bit stream, which is then further subjected to bit stream truncation according to the choice of the designer to generate the hardware security constraint that needs to be digitally implanted into the DSP. And this finally produces a stego embedded DSP core as an output. Okay, now this slide actually talks about the register or color allocation table, which is often known as colored interval graph representation. So we have, for example, the number of control steps, and we have these different types of registers, which are pink, indigo, violet, green, and so on till black. And these are the secret constraints shown in the orange table here, which actually represent the secret constraints that are obtained after the bit stream, either through biometric fingerprinting or through steganography or through watermarking is obtained. And what it means is that basically if we have a pairing between S0 and S2, that means these two storage variables cannot be executed by the same register. That is, these should be assigned to distinct registers. And that's exactly what we see here. This is the one which is before implanting, and this is the one which is after implanting. So for example, in case of S0, S2, they are anyways by default assigned to different registers, so we don't need to worry. However, for applications such as, for constraints such as S0, S8, they were all part of the pink register. But after we have done the local alterations, so S0 and S8 are now assigned to pink and indigo register. So that is how we do the local alterations for accommodating the secret constraints in the colored interval graph stage. So this circuit actually shows the RTL data path of an 8-point DCT. So 8-point DCT is a very widely used algorithm in JPEG compression in terms of 8x8 blocks. And it converts the spatial domain information into frequency domain. And this RTL data path is actually for an 8-point DCT, which is before implanting of stegography mark. And this is the RTL data path of an 8-point DCT after the stegography or stego mark is implanted into the design. As you can see, it is imperceptible and the stego mark is invisible. So just optically inspecting the surface doesn't let anybody find out where the secret stego marks are. Okay, now we move to another class of algorithms which are known as digital signature-based algorithms for IP code protection. So it uses a crypto hash function SHA-512 and crypto encryption function RSA, and along with the two encoding algorithms to produce a digital bit stream of the input information. So we have the pre-processing block 1, which produces the scheduled DFG and performs the assigning of the storage variables of the corresponding DSP application, and it generates a bit stream through the help of some encoding algorithm. Using SHA-512 block, we can calculate the digest of the bit stream, and from there, in the post-processing block 1, we can divide the bit stream digest into M blocks of size n bits. So basically M blocks as in like we could have, for example, 4 blocks of 120 bits each if the output is 512 bits in total. And then each of these 120-bit block is converted into its respective decimal value and fed into the RSA encryption block, where it is actually working in the presence of an RSA private key governed by the IP owner. And based on the output that we have got, we'll feed it into the post-processing block 2, which will construct a final bit stream by the individual encrypted decimal values and then concatenating it. And then in the encoding rule 2, we'll encode each of these bit values to produce a final hardware security constraints that gets implanted as a digital signature into the DSP design. So this slide just shows an example of one of the encodings. For example, if the operation number and the control steps have same parity, then it could be given an encoded bit value of 0, while if they are different parity, then it could be given a bit value of 1. And this just shows an example of the bit stream generated for a DCT code. For example, if you have 15 operation information in an 8-point DCT, then of course it will be a 15-bit generated number corresponding to that, because every operation has a respective bit value attached to it. So in this slide, what I'm trying to talk about basically is that this digital signature process offers several security properties. First is it offers collision resistance. Second is it offers deterministic property. And third, it is distributive in nature. So for every bit of the hash output is a function of every bit of the input bit stream. Okay. So therefore, based on the 3 values, the hashing is quite strong and robust, which will be further subjected to RS encryption and then concatenation at the respective points. This slide just shows an example of the RSA decimal input that we have taken, 128-bit, and the corresponding encrypted decimal output that we have got, and its respective binary equivalent. So this RSA is, as we know, is an asymmetric key encryption algorithm, where we have the private key and the public key. In case of digital signature, the private key is actually used for digitally signing the hashed information of the digest, and the public key is actually used for decryption purpose. Okay, so only the actual IP owner has knowledge of the decryption, decryption algorithm, because he can only decrypt it because he knows the point of concatenation that has been used while performing the encryption process. Okay, and the decryption process could work as follows: that if you apply the public key, we can decrypt it and get back to the hash, and then a second computed hash would be performed. And if both the hashes match each other, then we know that the signature has not been tampered with. And secondly, that only the actual IP owner would be able to perform decryption because he has the knowledge of the concatenation process. Okay, now going into the embedding stage. Now once we have the bit stream ready with us, then we can actually employ certain encoding rules as I've shown in this slide. For example, in case of bit 0, one of the possible encoding rules would be to append an artificial edge into the colored interval graph between the prime node pairs. For bit 1, appending an additional edge into the colored interval graph by adding an edge between even node pairs. Okay, so thereby by implanting these artificial constraints in the form of edges in the CIG, we would be able to accommodate the constraints into the CIG of the DSP application. So some data of the experimental results. For example, if you see the design cost function that we have, it's a normalized function of the latency and chip area. And by having this normalized function, we can get a design cost of the following DSP benchmarks, where with the increase in the digital signature size, beyond a certain point, the cost doesn't increase at all. So it remains quite constant, except for ARF, where it suddenly jumps from 60 to 120. In terms of the probability of coincidence, as the digital signature size increases, the probability of coincidence actually decreases, which indicates that the robustness of the algorithm is very strong, and the probability of arriving into this secure solution by default is very low. So one of the other classes of IP security or IP core protection algorithm is known as triple phase watermarking. Here what happens is we use a 7-variable encoding, and here the secret constraints are actually implanted into 3 different phases of electronic system level synthesis design. So the first phase is known as scheduling phase, which is responsible for watermark for phase 1. The second is hardware allocation phase, which is the watermark for phase 2. And third is hardware register allocation phase, which is responsible for watermark phase 3. And then these 3 are collectively appended together to form a triple phase watermark and embedded into the RTL description, okay, of the DSP application. So these are the designs that we have made for watermarked FIR and non-watermarked FIR at the RTL level. Again, by the optical inspection, there's no perceptible difference to find out where is the watermark information in the design. So therefore, this is known as invisible watermarking for hardware security. This shows one of the other applications that we have designed for obfuscated 3x3 image filter hardware with reconfigurable functionality. So this is used for performing image blurring, image sharpening, image embossing, and image edge detection. For example, we can use lapless edge detection. So this 3x3 filter kernel hardware, convolution kernel hardware that we have built is functionally reconfigurable. That is, by the application of the control input vector, this hardware can work as an image blurring filter, can work or as an image sharpening filter, can work or as an image edge detection filter, and so on. And the obfuscation part of this hardware circuit is performed by the application of tree-height transformation, which actually breaks the sequential operations of the data flow graph into parallel subcomputations, and also by the application of loop unrolling that actually increases the number of operations and therefore enhances the performance. We have also designed application-specific IPs for image blurring filter using the circuit that you've seen right on the top. This is for obfuscated blur filter. The second one is for obfuscated sharpening filter. Third one is for obfuscated vertical embossment, and then obfuscated horizontal embossment, and finally we have the obfuscated lapless edge detection. Okay, so each of these could also be devised or designed separately using the process of obfuscation and HLS. Okay, so now I'll move to the last part of my talk. So another example that we have another application that we have designed is for JPEG codec, compression decompression. Now the JPEG codec is an important part in many medical hardware or medical applications as part of the medical imaging systems. A dedicated JPEG compression decompression processor is employed to facilitate compression and decompression of images, and it is very important that the pixel values that is generated by the JPEG codec is authentic and non-tampered. Okay, how we can ensure that is because if you do not ensure that you come up with an authentic and correct pixel value, then it can result into wrong diagnosis of diseases. Okay, but JPEG, although being a lossy compression technique, is often used in medical applications as a hybrid compression mechanism, specifically for the for regions which are not diagnostically that important. Okay, so for regions of interest, it is lossless compression, and for the regions which are not diagnostically important, lossy compression can be used. So therefore, this becomes a hybrid compression. Now let me give you an example. For example, in case of CT scan for abdomen images, it could be like around 200 to 400 images. And each of these images could be 512 cross 512 pixels. And each of these pixels could have 16 bit of data. So roughly, this could amount to around 150 megabytes of data for a single patient. Okay, so therefore, this needs compression for local storage, as well as, when you want to do teleradiology and treatment, then also you need a lot of bandwidth to transfer that information from one hospital to another. So therefore, these JPEG codec processors lying underneath the medical imaging systems needs to be secured, either through the process of digital evidence to detect the counterfeited and the authentic hardware, as well as through obfuscation to thwart reverse engineering process during the design process itself. So, for example, if you have an unsecured JPEG codec processor and you use it as part of the medical imaging system for hybrid compression, then it may result into tampered pixel values generated. And but if, on the other hand, if you have a secured JPEG codec, then that can provide the first line of defense using obfuscation and the second line of defense using stegography or watermarking or biometric fingerprinting, and that will result into an authenticated and correct pixel value through the hardware. So in terms of the hardware threats, the Trojan insertion and the counterfeiting, they both could be thwarted through preventive control mechanisms, through structural obfuscation, which is responsible for converting the design and circuit into a non-interpretable form, which makes it difficult for an attacker to analyze and understand, so that he or she would not be able to secretly insert the malicious Trojan in a safe location. Thereby, this hinders reverse engineering and malicious logic insertion. And in case of cloning and counterfeiting, this can serve as a detective control using hardware stegography, as it enables to convert a normal design with a digitally implanted design, okay, through the form of digital evidence. So these are some of the CT scan images that were generated by our secure JPEG compression IP. For example, the first image is the input image, then we have the quantized image for Q90, and then we have the reconstructed image. So our secure JPEG compression IP, which is both an obfuscated IP as well as an IP that comprises of stego information, was successfully able to generate the correct pixel values for each of these CT scan images. Okay, thank you so much, and I really appreciate your time. I'd love to have questions from the audience.
So I would like to thank Dr. Singh for his very interesting talk. Unfortunately, I don't think we have any questions. So okay. We are going to proceed with our next speaker. So our next speaker is Dr. Madhusudan Singh. Dr. Singh is an associate professor in the School of Technology Studies of the Endicott College of International Studies at the Wusong University in South Korea. Before joining the university, he worked as a senior engineer in the Next Generation Research and Development Department at Samsung Display in Yongin City from March 2012 to April 2016, and as a research professor in the Yonsei Institute of Convergence Technology in the Yonsei University in South Korea from June 2016 to February 2018. Dr. Singh received his bachelor's and master's degree in computer application from the State Technical University and Master of Technology degree in IT from the Indian Institute of Information Technology, Allahabad, in India. He received his PhD from the Department of Ubiquitous IT of the Dongsaeo University in South Korea in 2012. Dr. Singh, thank you for speaking to us today. I'd like to hand over the microphone to you.
IEEE Computer Society and Kerry Cosby to carry on this, making this type of some new conference, virtual conference. So today's my topic was the cybersecurity. My topic is the cybersecurity for symbiotic vehicular network. So as I think we know about that vehicular network where is the vehicle communications is going on with each V2V, V2I, and there is a new word is coming like symbiotic. Symbiotic is not, we cannot say that it is a new word. It is a very old word. To first time it's coming from symbiotic means is the first use in ad hoc network, where we are connecting connecting the networks or nodes. They can update their features. They can connect each other and they will update features according to them. So they have some issues about the cybersecurities. Those I'm gonna be talking about today. So let's to know about what is the symbiotic network. So first use as an extension of ad hoc networks where devices make uses of each other's resources in order to extend their capability. So instead of the optimizing network parameters within the individual networks, symbiotic networking solution operates across the network boundaries. So it has not coming like in the normal network they are using for the network optimizations. They're talking about the network optimizations. So these symbiotic networks, they are providing nodes and their parameters are optimized between the networks and communal routing protocols are developed the leading for the more global optimizations for the scarce networks resources. So for example, we just talking about the example like symbiotic network as the data of sensor network along the highway is sent to the internet via intermediate mobile ad hoc networking and consisting of the vehicles. So they are using to those type of self-manage those their network to vehicle with the help of the network communications channels. Second, like in the vehicular network, how can we use this symbiotic vehicular network is the like V2V, V2I, vehicle to infrastructure communication will be more efficient and the reach of vehicular applications can be extended as their co-located network can assist the propagating the vehicular informations to one vehicle to another vehicle, their services, their environment, and their situations in that particular regions. So they can be change their informations to each others. So the symbiotic vehicular network should support self-organization, automatically reorganize itself to maintain and optimize the connectivity that required the support application in the dynamic network environments. So as in future, as we know that like a lot of research is going on the self-driving car and autonomous vehicle, those things. So once those vehicles are introducing in the real-time situations in the market, so that time we require that type of dynamic network. They can be managed, they can be changed their features according to each other's. They change their features, they change their compatibility, and they can make their automatically they can update their situations. They can take decision according to the situations. So new vehicles in networks should automatically and quickly detected and incorporated things. So that is the basics of the about the symbiotic vehicular networks. So now is our topic session topic is the cybersecurity of cyber physical system. So how can we use those features, cyber world and physical world? So here we can see that information technologies they're using for the security cultures, plus the physical features like vehicles, aeroplane, flight, whatever the transportations devices that can be nowadays they can be merged to each other and they will update their features things. So they're providing that we need to require them protect those cybersecurity things. So as we know that our vehicles are upgrading their day by day and they are changing. So they are explaining within the 5 level of their upgradation of development of the vehicles from the beginning 80s, 50s. They started from the vehicles automated things and till now what the status and how to development level they are defining. So they explain like here So level of vehicle automations, they will explain by the Society of Automotive Engineers, SAE, with their standard SAE J3016. So level 0, their drivers are only, there is conventional drivers, driver managers, all aspects of the speed directions, they can control by the human manually completely. Then level 2, they are assisted the drivers, receive the supports for the specialized tasks. For example, parking indicators, backlight, that features they are included in the level 2 stage. Second stage, they are using to partial automations. Their driver receives the support for the coping with the predefined scenario, services, traffic jam, warning, and those accident avoidance informations. And they will protect their vehicles, going to be more upgraded things. So currently they're working on the level 3, that is the conditional automations. So driver can be reluctance control to the automated system, but must be ready to take a back control. For example, like motorway, autopilot, those things. So as we can say that, like currently that is we are in the level 3 stage. The some of vehicles, they are providing this type of features, that conditional automations features, but still we have to update is the level 4 and level 5. Level 4 is the like significant automation, that is the majority of the journey may automate by the some drivers intervention may be required. For example, that is urban motoring. So we are belonging somewhere in the part between the level 3 and 4, those things that is going on, but still level 4 is a lot of work is required. And in the last level, that is level 5, there is a complete automation, like we don't do like no human interventions things. So like this is examples. So this is this is level 5 vehicles. They are connected with each and everything is connected with the Wi-Fi in the cyber world. So there's things are looking for that vehicles development. So as a symmetric network, that we talk about, the vehicle has the V2V communications, V2X communication, inside of vehicle communication is going on nowadays, is already working. So as we know about the V2V communication, where vehicle to vehicle communicate, we can send share their information, their location within the vehicles, and the vehicles to everything communication is provide the communication. This LTE, those for communication channel, through the communication channel we can communicate and we can share the whole reasons informations to each other's vehicles. And in vehicle communication, that is providing to getting the data from inside of the sensors, that is a CAN, control area network, electronic control units, sensors, and they will providing to those information, and according to those collecting information, they will decide what is the status of the inside of the vehicles. They can find out the fuel, there is some sensors are not working well, some accelerator and braking things. Though information can be based on those collecting data from these sensors. So they can decide that and we repair to those informations things. So these are the communications channels they're providing for our vehicular communication environment. The first is the dedicated short range communication channel, that is the IEEE standard association. They're providing 802.11p in 2010. That is IEEE standards for the information technology, that is provide a local and metropolitan area network. A specific requirement they defined in this standard for the wireless LAN medium access control, that is MAC, and physical layer. They were providing the specification amended. Then they again is amended in this amended is the amended 6, that is provide a wireless access in vehicular environment. That is another new vehicular communication algorithm or protocol they are providing now. They're working on this. They worked on that one, they developed and added in the amended 6. So these are the channels. As here we can see, they started from the channels as for 172 service channels, 172 to between the 184. So it will belongs between the 5.85 megahertz to 5.925 megahertz, where 5.7 to 5 megahertz to 5.85 is will talking about the Wi-Fi band. Then 5.8 to 5.9, they will using the gigahertz and more connectivity from the Wi-Fi and the cellular network communications, those things. And they are using these channels like 5.9 to 5 to 7.1 for the future use. For when the self-driving car and autonomous vehicle will becomes, then they will gonna be talk about these features. So that is, we talk about the amended 6, that vehicular access in the vehicular environment, that is called the WAVE. So it involves the two IEEE standard, that is 1609 high layer protocols and 802.11p protocols. They will mix with that, combine with those things and find it their informations, like 1609.1 that is using for the resource one. And in the web application, they are defining another specifically they are considered about the security. They think that yes, security is the important for this in this section in the vehicular communication environment. So they introduced in their amended 6, and they will start the working on this 1609.2 for the specify that protocol for the security purpose. Third, we have the 1609.3. They propose for the vehicular networking. How can they connect to vehicles to vehicle, and how do they connection the network vehicular network gonna be work? They specify, they make the standard for in the IEEE 1609.3. And in last one, 1609.4, they will using for the multi-channel operations for the physical and MAC layer, like 802, IEEE 802.11p things. So this is the common network where they're gonna be used those things. So these are the security, talking about the security issues. So here we can see that they are require the security in each and every level. Even though like when vehicle to vehicle, they are communicating to each others, then they need the vehicle secure data, privacy, authentication and authorization informations, and they need to verify that what information is receiving and what information is delivering, they are not modified, those things. Even though they are going to connect it with the communication channel through the Wi-Fi hotspot or DSRC or consumer network Wi-Fi hotspot and other things, so they require to be much the secure communications between those environment. And this, after that, they have the communication services they provided for the fog computing, and they will connect with the cloud, vehicular cloud network. So vehicular cloud network, they have stored the all systems, transportation rules, regulations, and their services, subscription-based services. So they are providing to those informations for to the vehicles with a secure channel. So where we require the secure channels to, so in the beginning of like automotive, in the cybersecurity perspectives, we require the security is not from the process. It is the product. When we start the manufacturing the product, then from the beginning of that product, we need to think about each and every level. We need to think as a make to design for the security point of view. So as a design level, we have to design software and hardware. For the automotive cybersecurity, we need to create the trusted platform. We need to ensure that interoperability of the vehicles to confirm the standard in automotive cybersecurity is what the security approach is and what the algorithm hardware we are using. They must be according to standards. They match the standard of their network. They can follow those things. So that belongs for the like design purposes. Can we also talk about that? It is we're talking about the inside of vehicle security. We're talking about the inside of the vehicle. Second, we have the build. After build, then we need to think about the security to build the secure communication environment, to develop the dynamic environment where vehicle gonna be talk about the anything infrastructures like traffic signals from the vehicles, from the anything else. So we require those things. So those things we require to communicate that information. We need to think about that. Then last one, we have the services, like what type of services vehicles are going to be used. So we can protect those services for the vehicles. So to ensure the security architecture for the connected vehicles, we need to control vulnerabilities and pre and post threat, during the communication, during this using the services, before the using services, before, after the using services, what type of risk happening that we need to think about that to register for the any applications or any services to use in the vehicle. So to allow users to use the services to low risk things. So the goals are the securing contents, authorizing access, authenticate users, message integrity. We need to provide this all protections, the security requirements we need to fulfill. That's why we need to achieve the all security methods for our vehicles. So this we need to think about the each level of the security. We need to provide the security for the each and every level things. So these are some attacks can be possible. That is example. These are some examples of the attacks for bogus information attacks, where the attackers can be transmit multiple bogus informations within a network, and they will ask that to, like, there can be happen with some greedy driver. He want to be clear their traffic, so he can just broadcast any messages to some wrong messages in the network, within the network. So this, for example, like these images, then attacker transmit bogus information vehicular in network and influence the driver decisions. Then we have disrupt the VANET, denial of the services. So in here, attackers to try create the artificial network congestion by the broadcasting too many messages and jamming the net communication channels. Then we have the vehicle data integrity. So data manipulation, we need to find what the information is receiving to between the going between two vehicles. They must be the verify those informations to they are not manipulated data, they are real data. Masquerading attack, that is the active attack, attempts to pretend to be the another driver by using to fake identities and can provoke the malicious objectives. Sorry. So attackers with the malicious objectives attempt to pretend to be the another driver by using the fake identities. Though this type of some common attacks is going on after they, like, these are the not only the 4 type of attacks, there is a multiple attacks. I'm just using as examples these attacks for the network. So for this reason, the society of vehicular network, vehicular communications and transportation of government transportation, even though they are proposed a lot of standard security standards. For example, like that is the 2016, that is NHT, National Highway Transportation System. These are the USA government Department of the Transportation. They are issued this cybersecurity best practices modern standard documents project. And there is in the worldwide, there is a lot of project is going on, like Preserve, Evita, 2.3 to 3.1, 3.2, SAE, Society of Automotive Engineers. They are working on a lot of projects like Preserve. They are finding the security requirements. Evita, they will talking about the security requirements for the automotive onboard networks based on the dark side scenario. And third one, Evita 3.1, they are talking about security requirements, automotive onboard networks. From the dark side is the updated version of this thing. Then 3.2, they are talking about the security and trust model. How can we be secure and trusted about the data information is flowing in the network? Then talking about that one. And SAE is recommended for the security and privacy, the era of the next generation vehicles. So they, except these are the some projects, there is a lot of other organizations, they are working for the project like Script, Intel, Microsoft, Tesla, Toyota, and MIT. They are working of these cybersecurity projects they have. So these are the vehicular cybersecurity practices. They are some standard, and some projects are worked already done, and some projects are already going on. So each project have what the features, security features they are concentrating and they are talking in their project. So for example, that Department of Transportation HS 812014, they are talking about the readiness for the V2V technology applications. They design the system architecture. ISO 26262, they are talking about the system architectures and security assessment. That MISRA ISO 27001 and this ISO 26262, they are talking about the security assessment. So these are the some different projects and standard they are using or they are working in the security fields. So cybersecurity standard is the cybersecurity guidebook by Cyber Physical System is published January 2016 that by the SAE. So they identify and access cybersecurity threats related to the vehicles, design cybersecurity into cyber physical vehicle system throughout the entire development life cycle, provides the foundation of further standard development, significant increase in the level of open source activity in the automotive space. So here are here we are talking about the traditional vehicles and traditional security issues. So for this traditional security protection is not enough. It's still current time is the advanced vehicles. They have a lot of threats about the third-party apps, oversight, key fib, matching, personal data leakage, and those are a lot of the issues. Like some attacks I already talked about the previous slide. So these are some traditional security. They are not enough to protect the vehicles. So for that purpose, we had proposed this blockchain technologies for the traditional to how can we remove those traditional security issues like centralized architecture, heavy on resources, unable to protect data that is mobile, unable to handle large amounts of data at the same time, no access to vehicle history, and no distributed networks. So how can we protect those things with the blockchain technology? We had provided everyone about basics things about the know what is blockchain technology. So as we know that blockchain is decentralized architecture, low on the resource, able to protect data that is mobile, able to handle the large amount of data at the same time, access to vehicle history and distributed networks. How can they will gonna be use it? So let we explore something. So as we know, these are the four basic pillars of the every blockchain, or we can say that these are the basic characteristic of the blockchain technology. First, like distributed consensus, there is all party agrees to the network, verify the transaction, which is provide the trustability, liability, and authentication authorizations. Second, we have the distributed ledger, that is append only system of record, share, and across the business network that will provide the availability, retainability, and traceability of the whole vehicle's informations. Third, we have the cryptography. They're using the ensuring secure, authenticated, and verifiable network. That for, as we know that we are using the SHA things. So they will be providing the confidentiality, data encryptions, integrity, and no modifications. And last, we have the smart contract that will provide the terms embedded in the transactions database and executed with the transactions. So it will provide that trust, the negotiation process, and the final contract availability and trustability and non-repetitions things. So these all four features of blockchain, four features are there providing this protect the all secure vehicles, the basic securities, or we can say that what the type of secure, we talk about the attacks, they can provide those, they can protect with those attacks. So how can it work? Like blockchain technology process in like autonomous vehicle, we're talking about the, not the level 2 vehicles, we're talking about from the level 3 to level 5 vehicles. We have proposed from the as much as self-driving car and autonomous vehicles. There's blockchain technology. How come they're gonna be protect those things? So they have, for example, there is one vehicles, they are senders. The blockchain enable autonomous vehicle. They have informations, they broadcast those informations. Through the information they have using the crypto hashing, transmission, distributed and validate the information. And then within the network, with the help of cloud, vehicular cloud, their data transmission is committed to blockchain and miners are rewarded. So this blockchain server, we are talking about that some network that is cloud servers, and they are connected with the vehicles or these servers. So then receivers, we can get it after the verifying and rewarded the miners. They will, receiver can be get the informations for the verifications. Where we talk about the vehicular cloud is the hybrid technology that uses the vehicle resources such as computing, data storage, and internet decision making. Second, we have that miner. We talk about the miner. A miner is a blockchain-enabled vehicles that can validate to the data transmission in the network. So this is the simple process. How can it work? But there is still we have to think about how those features are going to be implemented in the in blockchain technology features going to implement in the vehicles, right? So here we have a proposed that is a trust bit reward based intelligent vehicle communications paper. There we talk about that laser. There is all information is going to store in the laser, and we have to hash functions. They can create from the Merkle tree to make the block to headers they will use. And we proposed also algorithm for the proof of driving. So that is consensus algorithm. We have proposed that proof of driving, because that if we going to use the proof of work and proof of other consensus algorithm, they have that lot of communications. They need a lot of communication powers and those things. So in here we use proof of driving to only verify that vehicles are in mobile form or in the static form. That can be verified that the vehicle is not the static, is not going to done by some attackers and those things. So we have proposed this proof of driving algorithm. There is a way to provide the functions, and we use the less nonce and find out their difficulties, means how many nonce we're going to use there. And then in the result, we get it the original proof of driving with the nonce and difficulties, and we get it the asset original proof of driving to successfully is result and then we get it the return back to that blockchain station that, okay, this vehicle has what is the condition, what is the status of that vehicles. So then we have also proposed for the smart contract, like who is going to involve in the network, our blockchain network. Those vehicles is not going to be anyone can be involved. We need to find out some trustable and those things. So if we create some smart contract, if they are agree with that according to our smart contract, then they're going to be entered in our network. So this is the whole process for our vehicular blockchain technology, blockchain methodology for the vehicular symbiotic vehicular network. So for here we have the video clips. So yeah, here you can see this is the traditional. We're talking about the traditional network. How can be this traditional network is working current time? The vehicle is coming and they are statistic and they are following with the signals with the help of the traffic signals. They move after the green light. They stand with the red light, but with the help of that is sometimes it's not working. They have a lot of issues. They don't know what the vehicle is coming. So for this, we have proposed this whole seamless communications. That is our next slide. That is showing that how to blockchain gonna be work. This is another video, and can I get it here? The Nicholas 69. Yeah. So for here we can find out the video. You can see there is vehicle is coming with the blockchain technology, and they are sharing their information to each others, and they will find out the vehicle speed. They can control vehicle speed based on their situation, based on their all environment and what information they are receiving, those things. So these are the blockchain based network. We have talked about that currently. So yeah. So here we have using to some reward based system. As we talk about the miner, we get the rewards. Then why we require that reward systems things? Because for the reward purpose, we have proposed intelligent vehicles trust point. That is the IVTP, which using the blockchain secure trusted communication based of blockchain server and store the vehicle hash ID and those informations to the server, and they will connect it to they will work for the each and communications. So why we are using for the reward purpose? Because in the vehicles, they are going to share the real information or wrong information. If they are sharing the wrong information, then how can vehicles be going to get the feedback? So reward points we are using to as several benefits for this IVTP. First benefit, we can verify the vehicles are the legal or not. They are signed their smart contract or not. they are in our network. Second, we have to propose those IVTP. They can be work for that things to, how can be they were gonna be like in the future, there is a vehicle gonna be resale. They don't need to show that their whole data. They just provide their IVTP information that this is my IVTP. They can verify, okay, as much as vehicle has the trust point, that is the more reliable and trusted vehicles, and they have according to cost, they can use it, resell. Second, we have to insurance scheme. Like currently what happened, if we are using the vehicle, we are going to use the vehicle, we are paying whole insurance for the whole year, but in the whole year we are not driving, right? Every day and every hours we are not driving. We are driving only few of hours. For example, if I'm using to my car from my office to home, I'm just going to for the only weekdays, but we are paying for the whole year's amount of the insurance. So with the help of this IVTP, we can claim that whenever we are moving and whenever we are drive, those information will be provided with the help of IVTP, can be insurance to the insurance company, and we can ask them to reduce their amount of the payment, how much we need to plan. So these are the benefit for our reward systems for the IVTP, that trust point. So we have, but still these are I just talk about the simple blockchain implementations, but still they have a lot of issues like conjunctions of the significant amount of power. If we use only single blockchain, then if we are just simply talk about them. Second, we have the requires large size of data servers to manage information in real time. In the only one server of the blockchain is not possible to manage those things. Third, we have the storage of data needs to store for the long periods of time, more than the 2 years. So management of data exchange is mobile and dynamic environment is difficult to manage things. So for this, we have to propose another step. We have improved. That is another step of our blockchain mechanism. We are proposed to two blockchain server. One is the LDB and another one is the MB. That LDB is the local dynamic blockchain server that we can install in the one local region or two traffic situations, two local traffic location. And then we have another one that is the main blockchain server that can be connected with the several traffic systems. So local dynamic blockchain server we can using to the dynamically. We can store their information only for the few weeks, only for the few months. And after that, once they are gonna be full, they are automatically they're gonna be update their data. They reduce, they will delete the previous data and they will update it to new data things. And main blockchain server we have gonna be stored as a summary event. What is happening in that particular region and particular local region, that will be gonna be stored in the main blockchain. So that can be managed for the data management for the lot of vehicles there coming on some particular region. So a lot of data is going to generate. So those data generation we have just stored as a summary event based information in the main blockchain, and that local dynamic blockchain will be updated automatically going to what is going on the normal way. They are going up, coming and deleting and going and deleting things. So we have to did these implementations things in there. That is our framework for this blockchain, like main blockchain and local blockchain based blockchain dynamic based server. We had to propose those framework, and then we going to talk about that our branching systems. Like as I talk about the local dynamic blockchain, in some particular time there is a lot of traffic conjunctions. So in that case, handling those informations, they can automatically make it the branch, and within those branch they can be manage that informations things. So we had the patent about this proposed our branch based blockchain based vehicular communications. So there is a branching is performed by the local dynamic blockchain when the amount of traffic can be handled in the real time. The branching process is governed by these equations like delta T is the average time, which equals to the summations of difference between the mining time and the message broadcasting time over the total number of vehicles. Depends on that things. For example, we have provided the simulation result for this, our proposed idea. So that is looks like this one. So in the, for example, this is the intersection. There is a coming the fourth side, the all vehicle is coming. Now which vehicle is going to move in the same side if something happened? So how can we be, you're talking, we don't going to use to this traffic signal. That is where I already showed that is based on the blockchain video. So they is going to be manage their speed according to that. So this is like, we are talking about the state changes for the vehicles contain information about updates in the vehicles, position, velocity, acceleration, etc. The state change contains by the following field. That is the message broadcasting time. And then what is the which time, like IV vehicles ID, that is unique ID, which is randomly generated in order to avoid the mining for the similar block. Then we have to time, stamp denotes the time when the state was generated. And then we have the position contains the location of the vehicles, including the direction in which the vehicle is moving, which way the vehicle is moving, and that a state change, message broadcasts provide the state change of type records, various time, including the information on the start, acceleration, braking, turning, halting, and all these stage things. So these four values are included within the hash blocks and which must start with the specific nonce, that is number of zeros. So for example, that is the happening when talking about the last, these all vehicles are coming in the intersections. So there is the vehicle is first vehicle, second, and this process is coming to vehicle gonna be assigned. IV1 is the, as you work as a miner, and it will provide the list which vehicle is coming in the intersection first, and is based on the message receiving things. So based on that, they will provide to table which vehicle is going to move. According to that things, they are gonna be using this timestamp based reward distributions specifications. Then these are the reward point. For example, we can talk about those things. So here, and for the simulation, we have to, like, we don't have that self-driving car like intelligent vehicles, so we just use with the computers. So we as a use server and 4 computers for the as a vehicles, we assume that things, and we use for the calculation average time taken for the mining analysis in the seconds and number of the nonce. So for this, we have used 0, 1, 2, 3, 4, and 5 level of the nonce. So if we, as much as we are increasing the level of nonce, that is the number of zeros, the vehicle is going to be computational power is taking the higher and higher. So for this, we use to simulation for the level 3, only for 3 using the 3 0 for the before nonce for the nonce purpose. So for we get these results. So these are the talking about the average time for state change validation with the load of 2200 state change per minute is happening. So here we're talking about the branching based, 1 branch, 2 branches, and 4 branches. So it will becomes, this is for the, how can we see, these are the coming for the, in starting is going to very high, but as much as the data time is coming, that is going to slow. Second, we have to branch 2. So branch 2, and we'll talk about this. This is dark blue one is the branch 4, and this green one is branch 2. So we can see that branch 4 is still can be given the better result for that branch 2 things. So as we talk about that branch is the low, and then it will be giving to the better result. As much as we traffic is the low, then we get it the fast calculation stage change can be possible. Second, we have to some issues to how to push the blockchain in utilizing the same basic road and highway infrastructures to push for the blockchain solutions with what we required. So first, this benefit we can get it, the increase the number of passengers, we increase the amount of goods, increase the average speed, and it will decrease the congestion, decrease the accident and crashes, and decrease the carbon footprint, and is also going to reduce to the some highway infrastructures cost things. So these are the final remarks. Like blockchain technology, we talk about the overview, blockchain adoptions, approaches, and decentralized applications benefit that gonna be used things. And these are the some untouched issues. Still, we are required for the lot of research for this scalability of the blockchain, security, data immutability, energy consumptions, and late interoperability. So autonomous vehicle blockchain simulation is provide the intersection uses blockchain-based autonomous vehicle, and we get the simulation evolution, and research scope. As we talk about that, we have a lot of research scope is open for the blockchain one. And his last is conclusion. So today's talk, we talk about to automotive cybersecurity perspective to understand the problem and need to domain for the automotive technology. Cybersecurity challenges is manufacturing, in-vehicle communication, and automation. Cybersecurity, these are some organizations who are working for this field. And last, we had proposed to automotive blockchain technology, that is the make the build trust, distributed, decentralized data, and maintain the privacy, reliability, those things. And the last slide we have to this the subject matter expert that can be just proposed. I just finished our course, automotive cybersecurity course, that is IEEE Computer Society, is run by this and is available on the IEEE Explorer digital library and e-learning, IEEE Learning Network. So if anyone has this to getting the more details about the automotive cybersecurity things, so these are the 5 courses we have completed, and that is uploaded in the IEEE sites. So you guys can go and watch those videos, those lectures can be used. I hope that's gonna be useful for you. And this is about me. That is already Nicholas is introduced, so I'm not gonna be talk about 2 more things. And now that's thank you for this. So if you have any questions, then please let me know. Sorry for delay.
Okay. I would like to thank Dr. Singh for his very interesting talk. We have indeed some questions. So the first question is from Frederica Darema. What's the difference between symbiotic vehicular networks and interoperating networks?
Sorry, symbiotic vehicular network and?
Interoperating vehicular network.
Yeah. So interoperating network, as we talk about this symbiotic network is not for the only one particular locations wise. Interoperability network, that is operational is going on within the network, within the vehicle or within the network. So they can be managed to sharing those informations within some fixed reason, not fixed particular operations things, right? But in symbiotic network, that is we talk about to the network as ad hoc network and mobile based network that can be possible in the some larger scale gonna be happens. So that is the basic difference of this symbiotic network, vehicular network, and this interoperability vehicular network.
Yes, another question from Mohammad Sayat is that in this animated slide, you showed that there is a central server entity which handles authentication, or which somehow knows if the messages are received from its car. So why would you need a decentralized blockchain if you have a central server in the system?
So what video you're talking about? That is talking about my video, right? What I proposed those video.
Yes. So there a central entity arises, or is contained, which handles the messages that are sent to the different vehicles.
Yeah. So,
yes. So if you have a central entity, why you would need decentralized blockchain?
Yeah, why we need to decentralize blockchain, right? This is the main question is that. So we require the decentralized vehicular network because as I talk about this blockchain network, decentralized network, we have providing to several data, and that vehicle we can share with the insurance company, and we can protect to privacy also. If attacked, where is the attacker is targeted things. If attackers know that what is our taking point, so they are forcing to that location, right? So if once centralized network or centralized server is gonna be compromised with the attacker, so they can destroy the whole network. But in decentralized purpose, if we got it that okay, one network giving some wrong information, he's distributing and trying to destroy our network. So other networks can be block that node, that particular node, and they can work together. So there is no problem with there is no huge interruption between the network. Network going to work smoothly based on these decentralized features, right? So that's why we are required to decentralized network. If we are going to, that is the basic problems between the centralized one. If there is a center thing, so everyone is going to attack on that center. But if there is a way to provide that, okay, and once those in the decentralized network, one node is going to make the problem, then we can block them. And even though we are blocking them, we don't lose any data because those are all other data are stored in our blockchain server, other blockchain networks, nodes. So we can access those informations. So we don't have, but in the centralized section, if we are blocked that network, so it's destroy the whole network. So we need to wait for that, how to recover those information, those find things, right?
Okay, and final question, are there any standards or platforms that are important for your research, for the research that you have demonstrated?
For that, I actually, as I mentioned, I didn't use currently in the blockchain. We have to Ethereum and Hyperledger and some others platform. They are asking to use those things, but I didn't use any that platform. I'm just, as mentioned, I'm taking those features, basic 4 features of the blockchain technology, and I'm trying to involve those features in our network, in the vehicular network. We are trying to connect those network. So that's why we didn't use any platform, not Ethereum, not Hyperledger, not any other platform. We just use the blockchain features and we try to make the decentralized network based on those features. Yeah.
Okay, I would like to thank Dr. Singh again for his very interesting talk, and we should move on to our final speaker. So our final speaker is Dr. Swarup Bunya. Swarup Bunya received his Bachelor of Engineering with honors from the Jadavpur University in Kolkata. I'm sorry. And so Dr. Bunya received his Bachelor of Engineering with honors from the Jadavpur University in Kolkata, India, and the Master of Technology degree from the Indian Institute of Technology, Kharagpur. He has also received his PhD from the Purdue University. Dr. Bunya is a preeminent professor, director of the Warren B. Nelms Institute for the Connected World, and the Semoto Chair Professor of Internet of Things in the Department of Electrical and Computer Engineering at the University of Florida, Gainesville. Dr. Bunya has served as the T&A Strader Associate Professor of Electrical Engineering and Computer Science at Case Western Reserve University. He has over 20 years of research and development experience, with over 250 publications in peer-reviewed journals and premier conferences, and 10 edited or authored books. 2 of those are upcoming in the area of VLSI design, computer assistant design, and test techniques. I'm very happy to present now Dr. Bunya. Dr. Bunya, you are now welcome to begin your presentation.
Thank you. I hope you all can hear me well. So I really appreciate the opportunity. Thanks to IEEE Computer Society, thanks to Kerry in particular for making this arrangement. I'll be talking about Internet of Things, particularly Internet of Things security, which is a very important topic. It's a broad topic. So in that, I'll focus on the hardware aspect of Internet of Things security. Before I go into that, let me quickly introduce the institute where I belong to. I have the privilege to lead that institute as a director. This is Warren B. Nelms Institute for the Connected World in University of Florida. And in this institute, the focus is to develop Internet of Things technology as well as its applications in diverse areas. And when I talk about diverse areas, we are looking into application of Internet of Things technology in health, environment, agriculture, and in many other areas, including transportation and education. So these are the faces of the institute. There are about 50 members right now in the institute from 10 different colleges and departments across the University of Florida campus. I'm really proud to have all of them here. And they represent diverse areas of expertise, from analytics to sensing to communications to artificial intelligence, pretty much everything you can think of when you talk about Internet of Things technology. We have a number of new members who are joining, and we are looking for collaborators as well as sponsors for the institute constantly. So that's about the institute. It was established through generous donations of David Names, who is former Discover CEO and chairman, and also Sachio Semoto, a Japanese series entrepreneur who has established multiple companies. Both of them are alumnus of University of Florida, and through their generous donations, we have established the institute, which is at the forefront of developing IoT technology and using those to enable exciting applications for solving global problems. So maybe another time I'll talk about how IoT can solve global problems. So I'll give you examples. Right now we are developing technology, IoT technology, to deal with the COVID-19 situation. We are developing wearables that can monitor, detect, as well as mitigate the spread of COVID-19 disease. This is an exciting set of technologies which we are developing at the Institute. Maybe that will be a different topic I'll talk about at another time. Today, I'll focus on IoT security. And as I mentioned, in particular, I'll talk about the role of hardware, electronic hardware in IoT security. So one specific aspect of IoT security I will look at, as I mentioned, is that how hardware can play. And when I say hardware, we go from all the way chip to system of systems. So first let's talk about what is IoT. Now, I know that many people have different views of IoT, and I would like to define the IoT term to begin with so that we're on the same page. When we talk about IoT or Internet of Things, we basically think about the traditional embedded systems which are designed or optimized for specific applications, have a tight hardware-software integration, like your digital camera, like your personal digital assistant, MP3 player, which you had from a long time. So you take the embedded systems and then you add tremendous amount of connectivity to it. And these connectivities are within the devices of similar nature or within devices in the same layer, and I'll talk about that. And then these connectivities are also going to the next level, which is connection to the internet, right? And through the gateway. And then these connected set of devices are sprinkled with smartness or artificial intelligence to make them autonomous, for them to make intelligent decisions, right? So that's the step which you need to follow to make things IoT. And then finally, you make them interoperable. And why would you need that? Because these devices need to talk to each other, and they need to talk to the internet. They need to talk to the human users. That's why they have to be interoperable, and this interoperability has to be incorporated at different layers, from sensors to hardware to software to communication link, and that gives you the IoT. So that's the definition of IoT we are following. And in this definition, of course, I'll mention that there are many opportunities and, of course, challenges in dealing with issues of security and assurance. So this is the typical IoT architecture. I guess most of you have heard about this 4-layer IoT architecture. At the bottom of it, we have what we call edge devices or endpoint devices. These are the smart devices that do the actual job at the lowest level, and they do interact with the physical world. For example, if you think about a smart thermostat, that thermostat is sensing the temperature and humidity and other parameters of a house and making intelligent decisions on how to control the temperature. So these edge devices are connected among themselves, and as I mentioned, they're also connected to the internet through different gateways. So that's the next layer. So that's the network layer. And then we have the application layer, where you are running number of applications either in the edge devices or in the cloud, right? So basically the other four layers we have: things or edge devices, network, then cloud, and then applications. And interestingly, at each of these layers, there are a lot of interesting research opportunities. There are a lot of open challenges. So if you're interested in doing research in Internet of Things, you need to look at this architecture and see at each stages of the architecture, what are the research opportunities. And in this particular slide, I'm talking about the research opportunities in each of these layers. So I'll not go into all of them here. I'll just focus into a very specific aspect in this talk. That's the security of the IoT system, which spans the entire architecture. But as I said, I'll focus on only the hardware aspect of the security. Security spans the things layer or the edge devices layer, as I mentioned. It spans the network layer, cloud layer, and applications layer. But I'll be focusing on mostly on the things layer. So let's give you a little bit more background before we go into the security. So why security of IoT is important, and why we have new challenges with IoT security. So to understand that, let's give you some perspective. If you think about the Internet of Things paradigm today, these smart connected devices are going into everybody's hands. Literally, we are having a number of wearables like smartwatches. Even we are having smart tattoo on our body, and of course we are having tablets and other devices, other wearables and other devices in our homes and offices and cars. So these devices are going to be dominant in the upcoming years already, based on this web portal where this company Statista, a German company, which basically does market study. It's showing that in 2020 we have large number of in this year we have large number of smart connected devices already in the market. It's about 25 billion devices. And this number is going to increase significantly over the next 10, 20 years. They are predicting that by 2030, this number can be easily 50 billion devices. Now, if you have so many devices, and these devices are potentially being used by really naive people like my grandma or like my 5-year-old daughter, if they're using these devices, now you need to make them secure for people who do not know anything about security, who do not know much about how the digital systems work or talk to each other or interconnect with other devices of similar nature or heterogeneous nature. So that's a very, very interesting problem. Now, you do not have a system admin who knows everything about security, let's say firewall and other aspects of security, antivirus and things like that, and then they protect it for you. It's basically these devices have to be protected by the end users like my grandmom or like my daughter. And then the things which make it really, really complex is that these devices are working in a highly connected world. As I mentioned, these things are connected among themselves. In the previous talk, we heard about connected cars, right? So if the vehicles are connected, they're talking to each other. So that's one layer. But the connection is also happening with the internet, and then you have these devices connected to the cloud, right? So the question in terms of security is that how do you protect these really diverse or heterogeneous, highly complex computing systems in the hand of possibly naive users, as I mentioned, and which are operating in an environment where these billions of devices are talking to each other, right? So that's a very, very important security question. Now, what makes IoT very interesting and the security aspects of IoT is extremely challenging, a really, really fertile field of research are these fundamental issues. These are unique to IoT, and I will take a little bit of time to go through each of these issues one by one. So number one issue is that these devices connect with the physical world. For example, I talked about the smart thermostat, which controls the temperature for your home. This device is actually talking to you, and it's interacting with the physical world because it's sensing the temperature of your house and adjusting the temperature and also humidity. And similarly, think about a smart toaster or smart vehicle or smart refrigerator. All of them are interacting with the physical world. And the moment you have interaction with the physical world, and let's take another example like an autonomous vehicle, and that can be considered an example IoT device. For an autonomous vehicle or self-driving car, if you think about the security issues, because it interacts with the physical world, if you think about the security issues like somebody hacking into an autonomous vehicle, now that can run into an accident, and that accident can potentially kill people. So you see, security issues are immediately transforming into safety issues. So that's a very important aspect of IoT because they interact with the physical world. These devices have long, complex life cycle, which basically means that some of the devices like smart refrigerator, right, or smart vehicle, they would be there for 20 years probably, or 15 years, unlike the cell phone which you use and maybe every year or every 2 years you replace. So these devices will be there for a long time, and anytime you have devices in the field for, let's say, 20, 30 years, if it's a military device, then it will be probably there for 40 years. For such a long time, security requirements evolve. Attackers become smarter. They come up with new attacks. So you have to have a mechanism to deal with these attacks in a manner that's dynamic and adaptive. These devices are mass-produced in same configuration. There are millions of smart light bulbs. There are millions of smart refrigerators and fans. So if I'm the attacker, and if I know that all these devices are having exact same configuration, I can spend my time to reverse engineer one of these devices, understand the security issues, and then use that knowledge to hack into another device of the same kind. Many of these devices, I give you an example of smart light bulb, they are not intended to be connected to the internet, which basically means they do not have the right security protocol built in, and they may not have the right infrastructure in terms of hardware to implement those security protocols. So if that's the case, then of course, these devices would be very vulnerable to different kinds of hacking. And guess what? Because these devices are connected, if an attacker finds a weak link in the set of connected devices, the attacker would attack that weak link and use that to access the other devices, which might be more secure. But because you have a weak link now, the whole network connected system of smart devices are becoming vulnerable. Another point is that the communications are machine to machine. One smart light bulb is talking to, let's say, a smart refrigerator, or for example, refrigerator is talking to my smart autonomous vehicle, and it's asking it to bring some food from the grocery shop. So just thinking about the future. The point is that if a machine is talking to another machine, then there are a number of security issues. The typical authentication mechanisms which you use to log into your computer by putting your password, those kind of authentications do not work. And anytime you have a machine-to-machine communications, there are new vulnerabilities coming into pictures which attacker can exploit. I talked about physical connections with the physical world. But that also makes it vulnerable to physical attacks, which means that the attacker can physically modify the device. I'll give you an example of that later. And finally, we need to have a holistic view of IoT security as opposed to really looking into the security of edge devices or security of cloud or security of communication. Because any weak link in the whole architecture I talked about can compromise the entire IoT security, and that means it requires a significant rethinking on how IoT can be secure. So there are a number of example attacks we have looked at in our research lab. Professor Yergin, who is an expert in this area, he has looked at hundreds of IoT devices across which are used across the world, and we have pretty much hacked all of them. So that means that these devices have significant security vulnerabilities which can be exploited. And then I had to remove the videos because I didn't have enough time to show them. But I would like to mention here that IoT devices which you can buy in the market, almost all of them have significant vulnerabilities just because these devices are not really thought through in terms of the security requirements and in terms of what protections that should go into those devices. One of the important attacks that I will talk about today that happened few years ago, it's called Dyn cyber attack. I think many of you have heard about that. This is a cyber attack that really affected millions of users across America and across Europe for a large significant amount of time, and this and affected number of web services including Amazon and BBC and everything. The reason it happened is that the attackers could really compromise about millions of IoT edge devices. And the way they did that is that they figured out that these IP cameras and baby monitors and residential gateways, these IoT devices, they come with a default password. And if you are like me, you do not change those default passwords. And these attackers came to know about these default passwords for about 60 IoT devices. And then they created a malware called Mirai botnet. And this malware were injected in close to millions of these IoT devices. You can see it's called a botnet attack. And then these compromised IoT devices really acted as an army of internet army of IoT devices which can affect a DNS system or domain name system, where this company Dyn was converting the domain names into IP addresses, and these compromised devices now were making a number of fake IP requests, fake DNS conversion requests from millions of IP addresses, and that really brought the entire internet down in significant part of US and Europe. And that's the kind of attack that can happen in IoT because these devices are not secure enough. They're vulnerable to malware attacks, and they're also vulnerable to a number of hardware attacks. The rest of the talk, I'll focus on attacks on hardware. And this is a rather new domain because if you think about security, you most of the time think about security of the network or security of the software. But security of the hardware also is becoming a huge problem. Last 10 years has seen significant number of research activities across the globe on attacks on hardware and how electronic hardware can be made secure. But before I go into that, let's talk about what is hardware. Let's take a smart device. Let's take this thermostat which I mentioned. And this thermostat, which is responsible for controlling temperature of your house, and it can turn on the air conditioning on demand based on the temperature, based on your usage pattern, and things like that. If you take that device and if you break into it, then you will see we have printed circuit boards, right? So these printed circuit boards will integrate a number of microchips on it, and then inside that, among them, there will be at least one central processing unit. The same thing will happen if you take a cell phone, and then if you break it open, you will see that there's a printed circuit board, maybe one, maybe sometimes more than one, and then there are a number of chips. So if you look at the hardware part of it, we're not talking about software or communications or applications, anything like that here. If you look at the hardware part of it, then you can see there are 3 levels of hardware. System level hardware, where you talk about the entire systems, then printed circuit board, and then you have microchips. Now, security issues can affect all these layers, and I'll talk about some of the security issues which can happen in these layers. And the reason it's so important for hardware to be secure is that hardware is considered to be the root of trust, which means that everything from software to networking to communications and storing data, that depends on the security and trustworthiness of your hardware. And if that assumption is broken, then you have significant problem. Now, why there is a problem in hardware? Let me give you some quick description of that. If you think about how the hardware is manufactured today, or the entire life cycle of hardware, you go from a design specification, and that goes to the IC or integrated circuit design house like Intel or Qualcomm or Broadcom or Samsung, and then they design the integrated circuit. They send it to foundry or fabrication facility, and then they create OFR. These are typically 12-inch circular silicon disk, which has number of chips on it or integrated circuits on it. These are now assembled and packaged. Finally, they create and test it, and finally they create printed circuit board from this. They put firmware on it, and then eventually it comes into a system, right? And many of these stages can be untrusted, which means that you do not know what tools are being used, who are doing that, and then what components are also being used in those stages. Because of that, there can be hacker in all these stages, and they can compromise the trustworthiness of the hardware. Now, what can happen in each of these stages? Let's quickly look at that. If you think about the system on chip life cycle, typically it goes from IP vendors or intellectual property vendors giving the IP, then system on chip design house building the system on chip design, then as I mentioned, it goes to foundry, and then eventually it's deployed. At these stages, there are a number of significant attacks can happen. For example, in the IP vendor house, an attacker can insert a malicious circuit into the IP. In system on chip design house, the IP can be pirated, or a malicious circuit can be inserted. Foundry has the entire design in their hand. A rogue person in the foundry can do pretty much anything they want with that design. So they can implant a Trojan, which is a malicious alteration. They can overproduce, so they can clone, they can do piracy. All those things are possible. And then during deployment, there are several attacks that can happen. For example, somebody can try to extract the secret from stored inside your chip, like the cryptographic secret, which is used for secure communications and secure storage. They can also try to do reverse engineering and cloning or do physical attacks. So to deal with these problems, in our research lab, and of course several other researchers, they are developing solutions to have targeted design and verification approaches that can prevent these attacks, or that can detect these attacks if that happen, right? So I'll talk about some of the solutions today. But just to let you know that attacks on hardware can be really devastating. So this is a slide which I borrowed from Semiconductor Research Corporation. It shows you that if somebody can attack the hardware, let's say the Intel processor that goes into your let's say laptop or desktop or some other computers, if somebody can attack that, then they can really attack billions of devices. The impact can be much more significant. That's one aspect of the problem. The other aspect of the problem is that if they can attack the hardware, then it's hard to fix, because hardware is not patchable. We'll talk about a solution where we introduce a concept of patching hardware. But typically, hardware is not patchable. You patch your software, you install fixes. Many of them are security fixes. But hardware is not patchable. That's why it's not fixable. So if you find a problem with hardware, then basically you have to throw it away. That's why the impact can be huge. On the other hand, if you look at the security attacks at the operating system level or application level or user level, that's significantly less. Even though they are all important attack modalities, but the relative impact on hardware attack can be way more significant than the software attack, and this particular slide conveys that point. So coming to hardware attacks, one of the attacks that is becoming very dominant is counterfeiting. The attacker is basically either copying the design and creating fake chips. I know that a few years ago when I was buying Intel chips from some places, some markets, we found fake Intel processors, and it's true for other processors and other ICs from other companies. But the point is that this trend is actually growing. Electronics companies lose about $100 billion every year in counterfeiting. So it's becoming a huge problem. And these counterfeits can be of different types. They can be cloned products. They can be products which are overproduced in a foundry, out of spec or defective products which are coming into the supply chain. And then another huge percentage or a huge percentage of these counterfeit chips are recycled ones, which means that, let's say you use your cell phone and you kind of throw it away after a couple of years, but the cell phone has a number of valuable chips or ICs in it, right? So it goes to some black market, and there are people who will take those PCBs and then take out the chips, do some mechanical chemical polishing, and then bring it back to the market. So that's a huge problem. Recycling is a problem to deal with, and we have developed several solutions like other groups to deal with the problem. And then, as I mentioned, cloning, where they just copy your design and then make a clone. That's becoming also a huge problem. I'll not talk about too much on that because I think all of you are aware about that. There are some really critical examples of cloning where they cloned a router, they cloned a flash, they also cloned the engine control unit, PCB, in a Honda car, which is a serious problem, right? Okay, I'll talk about another interesting problem, which is another new problem. It's called hardware Trojan attack, and then this is such a huge attack that Michael Hayden, which is former CIA chief at US, he mentioned this problem as a problem from hell. In this attack, we are basically doing malicious alterations, or the attacker is doing malicious alterations here. So you take a design, attacker maliciously modifies the design so that the design can either create denial of service attack, which means it creates malfunction, or it can leak information from inside the chip. So you have the two modes of payloads for the attack, and the attack can be triggered by rare conditions from the chip. So this is a huge problem in detecting because this is not a traditional verification problem. And this requires a new domain of verification. We call it security verification because we are detecting malicious changes as opposed to bugs. And we are detecting unwanted functionality as opposed to functionality bounded by the specification of the design. So it's a huge verification challenge, very active field of research. And if you're interested, of course, you can start working on this. There are a lot of opportunities here. We developed a number of solutions, which I'll not go through, but it turns out that you can come up with functional verification as well as side channel verification, where you look at the effect of a malicious change in side channel parameter like power or electromagnetic emission or delay. Another attack that is becoming very significant for IoT, as I mentioned, is physical attack. In this case, attacker is accessing the printed circuit board of the device and can physically modify the printed circuit board. And there are many examples of that, particularly in gaming consoles and cable boxes or set-top boxes. And we have come up with a solution to deal with that problem, and this is called remote monitoring of the hardware. We create a fingerprint from the hardware by looking at the delay values across the JTAG path, which is the design for testability architecture in printed circuit boards. And these delay values are used to fingerprint, and we check it remotely to figure out if somebody has tampered the hardware of an IoT device. And it's a very powerful technique patented by our department. A number of companies are in the process of commercializing that. So I'll just talk about just a few new ideas. One is called hardware patch. We have talked about software patch, but what about hardware? We had a paper in IEEE Spectrum a year ago on hardware patch. In this case, what we are doing is that we are coming up with a hardware which is patchable. As I mentioned, the security requirements evolve over time. If it changes or a new bug surfaces at the hardware level, how do you fix it? So come up with an idea of creating a reconfigurable block inside a chip which can be updated, and this block implements what we call security brain. That means the most essential features of security in the chip is implemented in that security brain, which is reconfigurable, and we can configure that securely during deployment. And I will not go into details about how that is done. The paper lists everything. This is published in IEEE Spectrum, and there are a number of papers in different journals. The idea here is that to come up with a reconfigurable fabric, as I mentioned, called infrastructure IP for security, to do that. So this is pretty much the entire talk I have. In summary, if you really want to make IoT secure, and I'm just focusing on hardware here, you need to come up with an integrative solution. The idea here is that if you just make the chip secure, that's not enough. You have to make the chip, the PCB, the firmware, the software, everything secure. That's number one. Number two is that even for making each of these components secure, you need to combine design solutions with security validation solutions with runtime monitoring solutions. Only then you can have a secure and trustworthy Internet of Things. So with that, I'll stop here and we'll see if you have any question. I really thank my collaborators and industry sponsors, government sponsors who have really helped me to come up with these research activities. I also thank again IEEE Computer Society and the organizers.
So I would like in turn to thank Dr. Buña for his very interesting talk. There is indeed a question that remains, and from Frederica D'Arema: how would you define cyber-physical systems? And if you could explain the term cyber-physical in computer science terms.
That's a very good question. So cyber-physical systems are systems which has cyber component and physical components. Cyber components are components which talks to the internet. Physical components are the components which talks to the physical world. And there are many examples of cyber-physical systems. Critical infrastructures and many large-scale industry fall into that regime. So I have to admit that these terms are loosely defined. So cyber-physical systems and Internet of Things, they intersect in some areas, and the gap between them is rapidly diminishing. So basically, cyber-physical systems have systems which are larger scales. It has to have cyber and physical components. IoT systems, on the other hand, even though they have physical components and significant sensing modalities integrated into it, they are not exactly those. They are not exactly the large-scale systems we are talking about. So they are mostly focusing on wearables and industrial monitors, even though we call our autonomous vehicle as an IoT, but that term is also very loosely defined.
Okay, and I believe that with this answer from Dr. Buña, our session wraps up, as we don't have other questions. I would like to again thank all the speakers and our audience, and also remind the audience and the speakers that the next session of this conference will be today at 10 a.m. US Eastern Time, that is 2 p.m. UTC, on the advancements in information security algorithm. And if you are interested in this presentation or any of the upcoming sessions of the conference, and you haven't already registered, you can do so, and you can find more information about the sessions on the conference website, which is tc.computer.org/dvp-conference/. So thank you.